Okay, so in this video, we're going to talk about how to calculate percent yield and what that tells you about your results. So percent yield allows you to assess your experimentally obtained data versus what stoichiometry tells you is possible to obtain. So when you're asked a question about percent yield, you're going to be given some sort of experimentally determined value, like in the lab, X amount was recovered. You're going to then compare that to what the maximum possible amount that you could have obtained if everything went perfectly based on the stoichiometry, which is really hard to get everything you're supposed to obtain. The math isn't hard. That sounded bad. But in the lab, to get the exact number of grams you're supposed to obtain is actually pretty difficult. There's a lot of human error involved. So our formula for percent yield is the actual yield, which is either going to be given in the problem or if we were doing a lab, determined in the lab, divided by the expected yield. This is the number that if everything goes perfectly, beautifully in your lab, stoichiometry says is possible for you to get. Times 100 is percent. Okay. And so that's going to generate a value. And so what does that mean? Well, if my answer is less than 100, what does that mean? I obtained less than the calculated value. So maybe my reaction didn't finish, or I had measurement error. I didn't put in as much reactant as I thought. Okay. If my answer is greater than 100, which can happen, I obtained more than stoichiometry says I should have. Maybe my reaction still didn't finish. Maybe my reactants weigh more than the product. Maybe a gas was generated, which causes the product to weigh less and it didn't finish. Or maybe there was some contamination. Or again, maybe human error is huge. Maybe I mismeasured something. But it is possible mathematically to get percent yield values that are less than 100, greater than 100, and if you're a unicorn, exactly 100. You can be asked to calculate percent yield with or without limiting reactant, meaning you can be given the situation where you have to do a limiting reactants problem first or not, and you will see it both ways. So let's go through an example. So the first one, determine the percent yield when 36.4 grams of NH3 reacts with excess oxygen if 41.8 grams of NO is produced. So let's unpack kind of what's going on here. My reactants are the NH3 and the oxygen. And this is telling me I have excess oxygen, which means I have plenty, and the amount, the actual numerical value doesn't matter because I have enough. I have plenty. It's also another way of saying that this value here is my limiting reactant. It's the one that I need to concern myself with. So that's my starting point. My 41.8 grams of NO, that is what I obtained in the lab. This is my actual yield, meaning in terms of percent yield, that's what I'm going to compare to. So I have a note here. You have to turn your reagents into the same unit and substance as the substance that's given as my recovered product. So in this case, I'm going to have to do the stoichiometry to convert the 36.4 grams of NH3 into grams of NO so that I can compare those values. It goes back to that apples and apples versus apples and oranges conversation we had in the limiting reactants video. If I convert this to a different unit or substance than what I have here, I can't compare them. So I have to make sure that I'm converting to the correct thing. So let's just dive into this one. The stoichiometry is no different. It's just kind of the step that comes after. So 36.4 grams NH3 times 1 mole NH3 over 17.034 grams NH3 times, I'm going to NO, so 4 moles NO over 4 moles NH3 times the molar mass of NO, which is 30.01 grams NO over 1 mole NO. All right, so let's make this easy for ourselves. This cancels, and so 36.4, let me move this up so you can see, 36.4 times 30 divided by 17.034. So 64.128 ... grams. I'm going to keep the whole number there because this value is not my final answer. The percent yield is my final answer. So I'm going to sig fig at the very last step. So I'm going to just keep this whole number in my calculator and roll it right into the next part. So how do I set up the percent yield portion? 41.8 is what I actually recovered. So that goes on top, divided by what stoichiometry says I could get. 64.128 ... That whole number times 100 is the percent. So I'm going to keep the whole number in my calculator, and I'm going to go 41.8 divided by second answer times 100. All right, so 65.18167,937. So let's look. I have 3 sig figs here and 3 here, so my answer can have 3. So 65 point, the 8's going to round over, so 65.2%. So I recovered in the lab with that 41.8 grams, 65.2% of everything I could have possibly recovered, which isn't all that bad. All right. So the other way you can see this is if there is a limiting reactants problem first. All that means that's different is I'm going to do 2 problems like this. I'm going to pick the lower one, and that's the one that I plug into percent yield. So let's look at one of those. Determine the percent yield for the reaction if 8.45 grams of Na reacts with 5.3 grams of O2 and 6.35 grams of Na2O2 is recovered. So this is my actual, and these are my 2 reactants. So I'm going to take both of those 2 reactants, convert them to grams of Na2O2, pick the smaller one, and plug into my percent yield equation. So first thing I need to do is figure out my limiting reactants portion. So 8.45 grams of Na times 1 mole Na over 22.99 grams of Na times 1 mole of Na2O2 over 2 moles Na times 77.98 grams Na2O2 over 1 mole Na2O2. And this is a good time to say is make sure the equations are balanced. I knew going in that these equations were balanced because coefficients were already there. Always make sure you double check. You know, I'm not going to be that kind on a worksheet. All right, so let's see what we get here. Let's see, 8.45 times 77.98 divided by 22.99 times 2. So 14.308 ... All right, so now let's check the other side. 5.3 grams O2 times 1 mole O2 over 32.00 grams O2 times 1 mole Na2O2 over 1 mole O2 times 77.98 grams Na2O2 over 1 mole Na2O2. Okay, so let's see. 5.3 times 77.98 divided by 32.00. 12.9154. All right, so let's evaluate what we got. I can't make 14 and change if I'm going to run out of the O2 when I hit 12. So this is not possible. This is my limiting reactant. Therefore, this is the one that I'm going to need to use when I do my percent yield. So how much did I actually obtain? 6.35 divided by what I could have obtained, 12.9154, that whole number in the calculator times 100. So 6.35 divided by that number times 100. All right, now let's check out my sig figs. The oxygen, which is what I'm using, only had 2. The recovered had 3, so I can only use 2, so this is going to be 49. So 49% is what I recovered. Okay. So you're going to see the same thing. Make sure you identify what is your actual recovered versus what are your limiting reagents or your reagent piece.